So welcome everyone to this afternoon session. We'll have the first talk by Luca Biferale, and then with respect to the program, there will be a short session in memory of Professor Narasimha, who passed away last night. It will be a short session with a couple of short talks in memory, and then there will be the talk by Alexei Meilibave. So first talk for the afternoon is Luca Biferale, who will be talking from the University of Rome, who will be talking about applications of reinforcement learning and machine learning to turbulence.
Okay. So thank you very much. Thank you to everybody, Rahul, Shamridi, all the organizers, and Massimo for chair. I will tell you a few. So I prepared a couple of sub-talks, indeed 2 talks, in some sense, about 2 topics. That are 2 recent explorations that we did with my collaborators and friends in Rome, and not only in Rome, indeed. You see the names here down. It's, I mean, this is going to be a couple of joint works with Fabio Bonaccorso, who is a postdoc at the Italian Institute of Technology, with Michele Buzzicotti, who is a researcher in the Department of Physics in my university in Rome, and with Patrizio Clark Di Leoni, who is now at Johns Hopkins University, and with Lucaita Gastia, who is a PhD student with me in Rome, and a former student of Shamridi, indeed, in Bangalore. So I will present a couple of results about 2 attempts that we did recently in trying to apply machine learning and reinforcement learning tools to quantitative problems in turbulence. And our aim was really very empirical. I mean, we just wanted to see how much more or less standard but state-of-the-art tools that are used by the AI community can be just taken and applied blindly, more or less blindly. I mean, we did very small developments on the algorithms to problems that we are used to try to attack using the equation of motion. And I mean, I will speak about 2 main subjects. The first one is about data assimilation, that if you want to translate in terms of computer vision, the community, I would call it an inpainting, that is the need to repaint, to fill gaps in images. And I will present you both results using brute force data-driven tools, just machine learning without any knowledge of the equation of motion, and I will try to compare those results with other results obtained on the other end using heavily the equation of motion, that is implementing nudging to assimilate data in turbulence, that is using an explicitly forced expression of the Navier-Stokes equations. And then the second part of the talk is more devoted to Lagrangian applications, and this is done indeed with the same folk of people before, but with the addition also of Christian Gustafsson, who is a researcher at the University of Gothenburg now. And the second part of the talk will be, on the other end, as I say, the more focus on Lagrangian aspects, and in particular issues connected to the optimal navigation in complex flows, in chaotic flows. In our case, it will be a 2-dimensional time-dependent turbulent flows, where for optimal navigation, I mean trying to understand if we can implement in a efficient way machine learning tools to navigate from point A to point B in the shortest possible time, even in the presence of a strongly chaotic and mixing flow like a turbulent 2-dimensional turbulent flows. So just very briefly, my motivation. I mean, there are many motivations. There are, I mean, in particular concerning the data simulation, there are many motivations coming from people working on weather forecast, in particular, but also many other applications of people that are working with satellite images, and also experimental people working on PIV reconstruction and things like that. My motivation, I mean, our motivation were a little bit more. Let's say fundamental oriented, that is, we wanted to play with these data simulation tools in order to have a probe on the how I call it, the future ranking, that is quality and quantity of data. I mean, we wanted to understand in typical turbulent configuration, what are the data that I needed to control, that I needed to measure, how many, and what kind of data I need to control in order to have a good reconstruction of the and a good hint on the physics, on the parameters, on the properties of the flow that I'm working on. And the typical questions, you know, I just listed a series of potential questions that were interesting for us. For instance, I mean, we wanted to understand if there is a ranking between the spatial and temporal data. That is, if it is better to collect data on time or on space, or if you which kind of fields, I mean, you need to control. It's better to control in order to achieve a given reconstruction of your flow. For instance, in present, I mean, very typical example in the case of, for the case of convection, if it is better to measure temperature or velocity, or what you can say about one of the field if you know only information, so partial informations on the other. And then, I mean, you know, there are many other questions. The importance of boundaries. I mean, it's better to put your probes on the boundary or on the bulk. Of course, all these questions depends on the kind of application most of the time. And the goal is to somehow trying to understand. I mean, what are the key animals, right, that you need to control in order to have a good insight in your flow. It's a sort of empirical way to probe the important degrees of freedom in your field. And okay, here there is just a cartoon, right? The typical cases you want to understand. If you have a satellite image with clouds, I mean, how to guess what you don't measure, and what are the best tools to guess what you don't measure. Just to give you an idea, more quantitative but still colorful oriented. Here I show you, for instance, a data assimilation game that we played on a two-dimensional Rayleigh-Benard convection, where you have on the top left here the ground truth, on the top right what we are assuming to know. So it's just information about temperature on a subset of probes that are advected passively by the flow. And the question is how much I can reconstruct. I mean, how many probes do I need to reconstruct to fully synchronize with data? How many, if it is better to have probes, like in this case, that follow the flow, or to have fixed anemometers and things like that. So, okay, I don't think I need this slide for this audience. I mean, you know better than me what are the challenges in 2D and 3D. And so let me jump to a little bit another example of a question that it is starting to interest us. It's taken from a Lagrangian problem. It is well known. This is a typical slide that I show very frequently. This is the velocity evolution of one particle inside a turbulent flow, taken from a direct numerical simulation. And as you know, the evolution of the particle, this Lagrangian measurement, it's typically you can easily measure very intense fluctuations. For instance, you see that here the particle most of the time experience, let's say, mild fluctuations, but then from time to time enters in small vortical structures where it starts to oscillate as a crazy. Indeed, if you measure the acceleration, it's almost bimodal. You have order 1 signals and then fluctuations that are 100 times larger. And so these are extremely extreme events, rare but not so rare, in the sense that if you measure the PDF of the acceleration, for instance, of this signal, everybody knows that the PDF is strongly non-Gaussian in a turbulent flow, and it has the typical stretched exponential shape that I show here. And where even when you normalize the PDF with the root mean square, you can easily experience fluctuations up to 40, 50 times the standard deviation, which are of course rare, but not as rare as they could be or as rare as they would be in a Gaussian, for instance, statistics. And here, for instance, in this turbulent flow, 1 part every 10 to the 8 gives you a fluctuation that is 40 times the standard deviation. So these are extremely rare events, which would be nice to know how to predict or to control. Oops, doesn't change. Sorry, doesn't change slide. Oops, no, sorry. Okay, so these are extremely rare events. I mean, these are extreme events, not so rare. And a typical question that one would like to ask is, I mean, suppose you don't know, I mean, you don't measure all the signal, right? How much you can guess? I mean, how much you can predict, and how much you can extract from previous learning about the future, and eventually, if you know also the future, but not everywhere, you just miss a time window how good one can predict the existence or not of strong fluctuations in a region like that. So these are the kind of questions that we started to ask, and I mean empirically, I mean looking at the data and using the tools from the machine learning community. So just to be more precise, this is the first application that we investigated. It is summarized here, right? You have we're supposed to have a two-dimensional image extracted from some turbulent flow. I will be more precise in 1 minute. I mean, people that know will recognize immediately these are turbulent. These are two-dimensional images from a rotating turbulent flow, and we're supposed to have some missing gap. And that might be different size, a different distribution, could be even a very big gap, right? As large, almost as large as your domain. And the question is how much we can guess about the what we miss. Of course, it is not well posed. I mean, the answer is not unique. And the question is, I mean, again, what we can say either in a snapshot by snapshot or in a statistical sense. And so to a few words about the physics. I mean, we selected this rotating experiment as our first trial. Why rotating turbulence? Well, for many reasons. First of all, because we already had a very good database. It is not maybe a good reason, but for us it was. Second is because rotating turbulence is a very nice playground. It's as you probably know, it's a system that has both two-dimensional and three-dimensional physics inside. I mean, if the rotation is strong enough. Okay, now I have a message that the connection is weak. Can you hear me yet?
Yeah.
Yes, from time to time
okay,
it's kind of broken, the voice, but it's okay. We hear you. It slows down from time.
Okay, if it is too bad, please tell me. No. And so three-dimensional turbulence rotating turbulence is interesting because if rotation is strong enough, you have both big structures, which is, I mean, somehow we hope big coherent structures that might be not so difficult to reconstruct, but also they are immersed in a sea of strongly fluctuating three-dimensional properties. And if you look at the spectrum, we all know that we have both a direct and inverse energy cascade. So you have the formation of I mean, quasi-coherent two-dimensional columns and non-trivial small scales fluctuations. For instance, here I show the PDF of the vorticity field. You see normalized with its standard deviation. So you see that you have strongly non-Gaussian vorticity fluctuations, which is skewed, which has easily fluctuations up to 10 and 20 times the standard deviation. So it's three-dimensional turbulence, three-dimensional rotating turbulence is a little bit a mixture of very nice non-trivial features. It has power law spectrum, so the flow is order continuous. Also is not differentiable. You cannot hope to use smooth interpolating tools to guess what you miss. There is a huge range of scales excited. There are non-Gaussian fluctuations. So it's fundamental enough because there are no boundaries. I mean, it's relatively easy to simulate. You can have a very high statistical efficient and reliable database, but at the same time it's also, I mean, full nice non-trivial statistical and kinematical features. So what we did with our database with hundreds of thousands of images out of our database, and out of these two-dimensional images that were mainly taken, I mean, I will show you results only about images taken in the horizontal plane, so it's a horizontal cut of this volume. We started to play the game that I was telling you before, removing data and seeing how much state-of-the-art algorithms used by the computer vision community work on this kind of a very quantitative problem. I mean, of course, our quest is for quantitative results. I mean, we were not, we will not be able, we will not be happy just to have the, you know, some future. We would like really, and I will show you, to quantify in some precise way the reconstruction properties. So we use different tools. I will not enter in all the neural machines that we use, but I will show just one for the moment. We use, I mean, we mainly use these generative adversarial networks. What is the idea of a generative adversarial networks? It's very simple. You have it's a million degrees of freedom nonlinear fit, in some sense. And the idea is that I mean, the way we use it was to give in input the three components of the velocity field on one plane, and with a big gap, for instance, in the middle, and then we have a machine that is made, it's adversarial in the sense that it is made of two machines that work one in opposition with the other. There is a first machine that is a generator, and the generator is able to take the image in the input and to give you a guess for what is the output. And you train the generator minimizing a cost, and the cost is simply the L2 norm. The L2 norm between what you generate and the ground truth. Of course, it's a supervised learning. You need to know, you need to have a training data set where you know the ground truth, right? So you use this, so out of the 300,000 images, we selected a subset, it was almost 100,000 images that we use as for training. And so we have the generator that is just this nonlinear, strongly nonlinear interpolator that gives you a guess. The guess is, and the generator is trained with two costs. Indeed, one part of the cost is just the L2 norm, how far you are from the ground truth. And then next to the generator, I mean, aside to the generator, you put also a discriminator that is another network, which on the other end has again has in inputs either the image generated by your generator or the ground truth. So you show to the discriminator alternatively either the ground truth, so the real turbulent configurations, or what you have generated. And the generator, sorry, the discriminator is trained simultaneously with the generator, such as to maximize a cost that is able to discriminate between the ground truth and not. So it will maximize an output that is one when you give the real turbulent image, and minus infinite or zero, sorry, when you give the real turbulent images, minus infinite when you give a wrong image. And you train the two simultaneously, you see, and then you give to the generator also a part of the cost of the discriminator, because the generator knows what the discriminator produce. And then you see, you try to, I mean, the generator will try to generate images that wants to fool the discriminator, and the discriminator simultaneously try to learn how to distinguish. So you hope that you reach an equilibrium where the discriminator will not be able to, is able to discriminate because it has been trained, but the generator is as good as to generate images that are almost undistinguishable for the discriminator, and therefore you have not only trained the generator to produce something realistic, but also that is as realistic as another machine will not be able to discriminate. And then you play this adversarial game until you reach some equilibrium. I mean, you cross your finger and you hope that you reach some equilibrium. And in our case, we were able to reach some equilibrium. Here I show you, for instance, the evolution of the cost, with the total cost of the generator during a training using 100,000 images. And you see that at some point, I mean, unfortunately, this figure is not log-log. I mean, in log-log, you should see that indeed is continuously decreasing the cost. And you see that the machine is at the beginning. If you use the network not trained enough, you fill the gap with something that is, I mean, easily to recognize that is fake. And then you use the machine trained at some later epoch. The machine starts to learn how to fill to feed the gap with something realistic. At the end, it is not. It is in general very good. To give you an idea of what do I mean? Okay, this is a movie indeed. Here I show you a movie of this in painting by using the machine trained at the end of the training section. So with the best, let's say, network that we were able to achieve. And then you freeze the network and you present, for instance, in this case, 6 GAPPY images that the network has never seen. So this is really validation with something never seen during the training. And this is just a quality, I don't know if it starts. It's just a qualitative feature for fun, and then you show how well the network is able to fill by using networks at different epochs during the training, and at the end you see that it will for all the six examples is filling with something that is very close. Not always. I will be more precise. Very close to what you have. With what was the ground truth. In order to be a little bit more quantitative, here again I show now the validation. So we have the network that is trained, and we provide new image damaged, and we wanted to check point-wise how good we were in reconstructing. Here, for instance, I show you the velocity profile along this cut. And the solid line is the ground truth, the dashed is the one generated. You see that sometimes, I mean, first of all, you see immediately that the velocity is rough. I mean, there are a lot of fluctuations, right? So it would be impossible let's say, by using a simple smooth interpolator to guess a field like that. And you see that most of the time, this is a case where, for instance, the generator was very good. I mean, it's slightly shifted, but I mean, apart from this shifting, it was really able to generate in a very big gap the real structures. And of course, the smaller the gap is, better the interpolation becomes. If the gaps are very small, the interpolation is almost perfect. This is the average L2 error. Along one vertical line for different horizontal position. So I mean, of course, where there is not the gap, the error is 0. Inside the gap, you have in average an error that is of the order of 10% maximum, 10–15% maximum, could be even smaller. And if the gaps are very small, it could be a few percent. Let me just comment that when I say very small, I mean, these gaps are small, but still larger than the viscous scale. So the flow is not smooth inside this gap. It's not very rough, but it's not perfectly smooth. It's not perfectly differentiable. Then, so I mean, I think we have a tool in the box. Consider that these are two-dimensional images. So it would be, I mean, it would be very hard. Oops, I don't know why it's frozen. Wait 1 second, sorry. Okay, so Let me show something even more quantitative in this slide. Here on the bottom right, you have the PDF of the L2 pointwise error. So it's just the norm of the velocity ground truth minus the one provided by the network. Of course, only inside the gap, because otherwise it's at 0. And you see that the PDF of the pointwise error normalized, of course. So it's a number that is of the order, it's in percentage, if you want. It's, when the gap is big, this is 1/2. It means it refers to this gap size. You have, yes, you have sometimes with 1/1000 errors that are relatively large, 70%. But most of the time, the most probable value is less than 10%. And if the gap is smaller, of course, you improve a lot. And if you are not interested in a pointwise reconstruction, the machine is almost perfect. Here I show you statistical properties. So this is the PDF of the entropy, and the other curve is the PDF of the velocity inside the gap again. And the red points are the true data, and the black are the data provided by the machine. And you see that statistically speaking, if you do not ask to have the right value in the right position, but you just ask to have the right statistical properties, the machine learns how to produce a two-dimensional rotating image perfectly, I would say. And these are the properties about the spectrum and so on and so forth. And other benchmarks, this is the PDF of the subgrid energy transfer. Again, it's a statistical check, just to be sure that you also have the right phase synchronization and the right structures that goes beyond intensity of something. Because if you see that we have also the real data, the black curves, and the one generated have exactly the same statistical fluctuations. Here on the top right, you have the fourth order structure function. In the inset, you have the third order structure function. These are all the kind of statistical checks that everyone from our community would ask, the machine to fulfill. And then here in the bottom part, you have a prediction on the maximum inside the configuration. So we didn't, it's a mixture between statistical and L2 error. We just ask ourselves how much good is the machine to predict what is the maximum value inside the GAPPY region, without asking it to also predict the exact position. And also in this case, the correlation with the ground truth is not that bad. So just to, so I think we have a tool, and just give me 5 minutes more because I promised to do it, to compare with equation-informed approach. I don't know if Idris is with us, but I'm going to use nudging. That is something that Idris worked a lot in the last few years. And so what is a way to reconstruct data using the equation of motion? Well, there are many different ways. One popular way that I like very much is this nudging approach that is used a lot by the community working in weather forecast. Indeed, is used also by in economy. Now, the Nobel Prize in Economy 2017 was awarded to an economist that introduced nudging in economy. And nudging is a very simple idea. Just give me 2 minutes to show. What is the idea is that suppose that you have data corrupted, right? For instance, like here, you have just data on a set of small points in your volume, or you have corrupted in Fourier space. You have just data on some frequencies, and then you want to guess the ground truth. So you want to reconstruct. It's a sort, it's a sort of super resolution, right? And so the idea is that if you know the equation that have generated the data, you can use the equation, you run a numerical simulation by forcing the equation with the known data. So you have a a Newtonian relaxation term here. And you input your information, so it's completely unbiased. I mean, it's unbiased, but you must know the equation, of course. You just input your data. You don't know anything about the statistics. The statistics, you hope that the statistics is produced by the evolution of the equation. So the Navier-Stokes will do the dirty job for you, will fill the gaps. Of course, this is, I mean, you must know the equation of motion. But I mean, you must know all the equation. I mean, you must know everything. It is not needed to know everything, because some information about the boundary condition, about the forcing, is nevertheless embedded on the data that you give. So you can even run the equation without the boundary condition and still get something that is reasonable. And so we compare, we did the same game with nudging. And now I don't want to spend too much time in describing the results or what is more efficient, less efficient. It's not really important, for at least for me in this moment. The message that I want to send is that if you repeat the same with nudging, you achieve more or less the same quality of the machine before. And the error that you commit is of the order of 10%, 5%. Depends on how many points you use. I mean, we didn't really then fine tune all the parameters. I mean, order of magnitude is the same error. Of course, the two tools are very different, right? I mean, in the generator, the machine, once you have trained, it gives you the result in 1 picosecond. I mean, put aside the time that you spent in training, then you have a new image, you have immediately the result. The nudging is the opposite. You don't need the training because you know the equation. So you can do it also even with only one image, but to get the results, you need to run the 3D simulation. I mean, with all the machinery of a real 3D simulation, which might be very, very, very tough. So I mean, there is a trade-off. I mean, there is no a better tool probably, but it's good to know that we have different tools. Last 10 minutes, 12 minutes, I'll speak about the other subject, the one concerning optimal navigation. Here we use a different machine, let's say AI tool. It's reinforcement learning. It's particularly suitable when you have time evolution, when you want to optimize strategies and policies that needs to be updated in time. And it's the kind of game that we played. I mean, even here there are many potential applications of optimal navigation. I'll give you one example that is very important. Massimo also knows a lot. I mean, he did similar things with gliders. That is optimizing trajectories of drifter for instance, on the surface of the ocean, right? And there are thousands of drifters that go around the ocean to measure temperature, salinity, and all other stuff. Most of the time they are passive. When they are passive, you cannot optimize anything, of course. But sometimes they are not passive. For instance, there is the ARGO project that has balloons, right? The drifter that can go also deep in the ocean. So you can decide the buoyancy of the drifter, such as you can also make a probe of salinity, temperature, and other properties at different depth. And these are let's say autonomous vehicles that you cannot completely control because they don't have strong engines. They must save energy. They stay on the surface of the ocean for years. So most of the time they have very small control. For instance, there is this drifter that has a drag that beyond the surface that allows it to feel the currents, the currents of the ocean at different depth. So you can control in some sense which kind of wind, which kind of currents is able to feel, to move. And it's I mean, extremely would be very nice to have the optimal way to control them, you know, to minimize diffusion or to move them according to some request. Of course, we didn't do anything strongly applied. We played with numerical tools, and the kind of optimal control that we started to look at is what is known under the name of Zermelo problem. It's a very simple problem. You have a flow. In our case, it's a time-dependent flow most of the time. I mean, we also use a time-independent flow, but I mean, let me speak about the time-dependent flow for the moment. And we want to move from position A to position B in the shortest optimal time. And what we supposed to be able to do? Well, we're supposed to follow this equation of motion. The velocity of our vessel is given by the underlying flow plus a control. And the control, in our case, in our game, is it has a fixed intensity, and you can only change the steering direction. And similar, by the way, similar questions have also been studied very recently by Rahul, Jeremy, and collaborators, and in this is cited here. And you see that the problem is, I mean, it would be impossible if V is very small, because if V is very small, you just go where the wind brings you, and there might not be paths that reach A and B, that connects A and B. It is trivial if V is very strong, because you just have to go on to steer on the direction of the target. And it is highly non-trivial when V is intermediate. And so we decided to work, of course, in the highly non-trivial regime. So we took V, the intensity of our control, a fraction of the maximum of the velocity of the flow. So in order to reach in the shortest possible time the target, you need to take advantage of the flow. So it's better, it will be better to learn where the flow is going, and to use the right wakes to reach the target if they exist. And so a very important point, because I will come back then later on, is that we tried to play a game that is robust. So the question is not only to find the shortest optimal path, but also to find a path that is robust against a small change in the initial condition, because otherwise it would be completely meaningless, right, and useless. So we tried to, the question that indeed we asked ourselves is, suppose you start from a small disk around the point A, what is the best policy to reach, the best steering policy to reach the target B? And the kind of game that we played was, as I said, the only action is choosing every instant of time which steering direction you can take. And of course, if you want to control, you must know something about the environment. And we're supposed to know only a coarse grain representation of our world. So we are in a grid world. We have a tiling of our two-dimensional space, and we suppose that the vessel knows in which of the tile it is. And we search for a policy, for an optimal policy that tell us, depending on which tile you are, what is the best direction that you have to take in order to get to the target in the shortest possible time. In order to optimize the policy, we use this reinforcement learning tool, which is very intuitive way. That is, you parameterize the policy in some way. In this case, in our case, it was a softmax policy with some functions that are parameterized in some functional space, and then you go and try to optimize the policy with trial and error, right? So you have a reward function that is just minus the total time it takes to go from A to B, and you want to optimize the policy such as the reward is maximum. So you start with a random policy, you go around, and you measure what is your reward, and then you back propagate this information by maximizing the reward and changing the parameters that parameterize your policy. And and you do it in a loop, right? You start to have a random policy, you get a reward, you see if the reward is good, you move the gradient such that you reinforce that kind of actions, and you go in this way. There are many different algorithms to do that. We use an actor-critic algorithm that moves both the policy and the best guess that you have at the moment of your total reward. These are technical details, not so important. I mean, we choose this approach because we wanted to explore it. I don't even know if it is optimal or not. I mean, there might be other reinforcement learning algorithms that might converge even quicker. We didn't explore. And here is just to give you during the training, right? You do thousands of these episodes. Here I show you the total reward. You see that you start with a very negative reward. When the policy is random, you move randomly, and then you start to optimize the policy until a point where you continue to train, but the reward doesn't improve. So you're supposed to have reached your optimal policy or close to optimality. I mean, at least a local optimal. Just to give you an idea here, I show you the trajectories that you would follow using policies that are not optimal at all. The green ones, you see that they go around, they move in a very, disorganized way. I mean, very few of them reach the target. And this is the PDF of the arrival time. So you have very long tails, so very bad performances. And you have a lot of failures. And then when you start to use policies, you start to improve the training. So use policies that are more and more optimal. You start to converge along some policies that are able to control in a non-trivial way. You see the blue one are almost optimal, the red one are even better. And these are navigation experiments taken with a policy that was already converged. Just to give you an idea, here I compare. In this movie, I show you once I got the final policy, the one that I supposed to be optimal. Again, I repeat, I trained it starting with random position in this small disk. So it is also optimal against small changes in the initial condition. I show you now hundreds of trajectories using the optimal policies that move from A and must reach B. And in blue, you have the trajectories optimized with the reinforcement learning policy. And in green, you have trajectories that are the trajectories that I call the trivial, naive trajectories, trivial policies, that are trajectories that just follow the direction of the target. I mean, the ones that you would use if you don't know what to do. Just look at the target and you go in that direction. You see that the blue ones, the one optimized, have two important features. First, they almost all of them reach the target, independent of the initial condition. You see that they have exploited the currents, the stream here, right? They really go and search for the stream, while the trivial ones, they are much more random, and not all of them reach the target. They reach the target with a distribution of time that is much broader, and you have definitely, they are definitely not optimal. I mean, the number of failures also is very large. So this is a very, I think, it shows that this reinforcement learning is able, given a flow, to control also a system that is strongly chaotic in a non-trivial way. Last 3 minutes, a comparison with optimal control on the other end. That is a slightly different problem. In this, at least as we play it. Maybe you can play also in the way that we did it, but we didn't know how to do it. That is, suppose now we know the equation exactly, we know the flow everywhere, right? And we know the exact initial position, the exact final position. Then if the flow is time independent, there is an exact solution to the Zermelo problem that you can obtain with optimal control. So you have a Lagrangian, the total Lagrangian is a total time, you minimize the Lagrangian with some constraints, and you end up with an equation for the steering angle at every instant of time. It must, if there is a solution that connects A with B, the one that connects with the shortest optimal time must follow this equation, which is strongly nonlinear, right? A is the gradients, right? But what is the problem? The problem is that you see the system, even if it is 2D and time independent, the flow, because you have a third actor that is the action. Indeed, the problem is three-dimensional and it might be chaotic. You might be strongly sensitive to the initial condition. Indeed, I show you for the time we tried this optimal control with one frozen snapshot of our 2D flow. And we just integrated the exact solution of the optimal control theory from A to reach B. And we did it with a shooting initial direction. I mean, it's highly non-trivial to find the right initial direction for theta. And I mean, we need to shoot 100,000 trajectories with all possible initial direction to find at least 10 that reach the target, because the system is strongly chaotic, strongly sensitive to the initial direction. So this is, I mean, a clear indication that if you don't have an algorithm that is able to be robust against randomness, either in the initial condition or with noise, I mean, in a flow like that, I mean, it's impossible to control in some sense. And here I compare a solution with reinforcement learning in this frozen flow with the ones from optimal navigation, optimal control. And again, you see the PDF of the arrival time. This is very reassuring. The reinforcement learning is finding the optimal solution. That is one of those that you find with optimal control, but it is much more robust, right? I mean, it is all attempts of the reinforcement learning reach more or less the target with the same total time, while the optimal control, as I said, being strongly sensitive to the initial condition, you have many failures, and the PDF is not so concentrated. So I think it's 45 minutes. So I think I stop here. I just give you, I mean, my feeling. There is, I mean, we have these tools based on big data, if you want, you know, thousands of training sections that are, I think, for some problems they are as quantitative as other tools that we are using in the past. It will be very good to have, you know, a combination, I think, of rigorous results and good data and good phenomenology to understand, I mean, to improve, to understand, I mean, which one is the best given some application. I think I stop here and I'm ready to take your questions. Thank you.
Thanks, Luca. Thanks very much. Is there any question? There's a question in the chat by Jonathan Skip. Maybe you want to turn on your microphone and ask the question.
Yes. Thank you very much. It's a very great and a unique talk. It's nice to see that you know, machine learning world is making its way into fluid dynamics. So my question is that is the nudging? I was just asking about the nudging case. I didn't quite get whether it's used to fill in the missing data at the same time snapshot, or is it used to forecast into the future of the flow by using the damaged data as a kind of initial condition? Yes, that's my question.
Yeah. Well, you can do both. You can do both. I mean, we did it only to refill the gap. And so we just, I mean, in this application, we did it only to refill the gap. So we just used one snapshot. So it's a frozen forcing, a frozen nudged forcing. And we don't know anything else except that damaged snapshot. And in this application, we used it only to refill the gap. Once you have refilled, of course, you can now use nudging. I mean, now it depends. If you have another configuration in the future, you can continue to nudge, right? And so try to synchronize the flow every time that you have some information. Otherwise, I mean, you can use as an initial condition, but then it's not a nudging anymore. You just use initial condition that you have prepared, and then you evolve Navier-Stokes.
Okay, yeah, great. Thank you. That clears it up. Thanks.
There's a question from the YouTube channel by Umberto Giurato from Nice. He's asking, is the neural network used for the generator a convolutional neural network?
Yes, it is. It is a convolutional neural network that we more or less picked from the computer vision community. I mean, the best, at least the most recent ones that they were using for, you know, in painting a picture of women or horses. And I have to say, frankly, we didn't really spend too much time in trying to change it. Even though I think it's a very interesting question. I mean, we miss at the moment a very clear understanding of, we have a very clear understanding of the complexity of the phenomenology of the turbulence, but we miss a matching, I think at least, a matching with the complexity of the machine, of the neural machine. and such as, I mean, to really understand how, you know, how many layers we need as a function of Reynolds number, how many, which kind of convolutional filters we need as a function of the turbulence that we want to reconstruct and things like that. I mean, this is very, let's say, dirty work, but that it should be done if we want to use in a systematic way this kind of tools.
I think it's very much connected to the next question by Baral. You want to turn your microphone on?
Thank you. Just a very classical question in this kind of machine learning experiment. How does it generalize outside of the precise data set it was trained on?
I don't know. I don't know. I mean, we tried. I mean, you can. For instance, for this in painting, you can try to be pretty general by training, for instance, changing the size of the the position of the damage is not important for us because we are periodic. But changing also the kind of you could train the network to be a little bit flexible, changing the size of the damage and things like that. We didn't try, but people in the computer vision do it a lot, and this is pretty generalized pretty well. I don't think it will generalize if you use a different flow. That's different structures. That's it will be very, very difficult.
Thank you.
A couple of comments by Idris.
Yes, thank you very much. Luca, can you show us the nudging scheme that you put in your transparencies?
You see it?
Yes. So G is sort of interpolate. What is G of V? It's sort
okay,
of
no. Yeah, G of V. G is a filter of V. V is the truth. G is a filter of V. Could be a spatial filter or a Fourier filter. So
yeah, but this. Wait a minute. So this Vn and V is the same V, or this is coming from information?
So Vn. Vn is the information that I give to my Navier-Stokes.
Yes, but then
there is an extra filter here.
Yes, but the initial value of this V has nothing to do with the initial value of the other thing. I think the scheme is really the way it's written. There is some issue with that.
The initial value of the real flow. You mean the one that I initialized?
Which you don't have. Which you don't have.
Of course. I start from zero. I wait. I mean, I have one time independent forcing here, and I start with V equal to 0 everywhere, and then it synchronizes and starts to oscillate around my GAPPY region.
So I think what you try, this Vn is not really is not exactly the G of V which you are simulating. This is an output from outside. Maybe you want to call it G of some reference solution U.
Sorry. I mean, this V is not the V that evolves in time.
Exactly. That's it.
Okay. Sorry. Okay, you're
now I understand. And this N is like a parameter. This N is a parameter. Correct?
Yes.
Okay, yes. Very good. So now let me make a comment. Now my comment.
Okay.
This scheme is what many people called it the nudging, and they tried all this. As you said, there's a long history, but this scheme is not the right one, and this will not converge. And let me tell you why, or let me mention, if I have a minute, how did we come to the nudging scheme to begin with? It was based on turbulence theory, because classical turbulence theory asserts that there are finite degrees of freedom in turbulent flows. And Foyash and Prodi in 1967 showed that if I know the low Fourier modes of the solution in 2D at least, then the solution will follow. And as a result, probably what has to be nudged is not Vn towards V, but some reference solution to the G of V. Namely, you have to match the filtered with the filtered, because here you have a leftover and it will never converge to the solution. And that's where basically our contribution was in comparison to what everybody was doing nudging, because there was no mathematical theory to support that. So there's a theorem which will tell you what it should be done. So this nudging is not the right nudging, unfortunately.
So what do you say? So sorry, say it again. You say that you want to solve the equation only for on the support of the field.
No. What I'm saying something. Luca, I'm saying something simple. You write your equation as is, but in the nudging should be coarse scale nudged toward coarse scales. Period. And what happens to the fine scales? They will follow.
Okay. Wait.
This is what we do. This is what we do.
No, but you have V. But you have V, not.
Okay.
Wait 1 second. Let me explain. This is what we do. I mean, I told you here there is an extra filter, G, that apply the nudging only on the position where we have the data.
Okay, good. I think we can move to the last question, which is Prasad Perlikar. You want to turn on?
Yeah, hi. So the question is that the data on which you are doing the machine learning or the nudging is strongly rotating turbulence data, right? Where you have a strong rotation. And so the field is very two-dimensional. The question I had was that if you didn't have rotation and you had just high in or even for your rotation data, if you looked at components which were perpendicular to the direction of rotations. So in the sense that, you know, VZ statistics. So instead of VX, if you look at VZ statistics, does that thing also reproduce equally well? Or if you were doing homogeneous isotropic turbulence, does that work equally well as, you know, the strongly rotating case that you have?
No, okay, there are two questions. So the first question is that if I apply to the vertical plane the same kind of inpainting, it works well. I mean, I have to train, of course, also on the vertical image.
Yeah,
it works well. For the three-dimensional case, it's a bit more complicated because if you want to be strongly turbulent and 3 dimensions, you need to supply a lot of data.
Okay.
Otherwise, you are too sparse. And I mean, we didn't try, but I am a bit pessimistic that you can really reconstruct a 3-dimensional configuration with this kind of machine if the flow is strongly turbulent. If the flow is smooth, there are already other examples and people have already done it.
Okay. All right. Thanks.
Thank you, Luca. Thanks so much.